In this video, we'll be working through a relatively challenging problem that is similar to the method of images problems that we solved in the previous series of videos, so I suggest watching those to get a brief background information for what is needed today. Today, we'll be working through a problem where we find the force on a positive charge Q that has a distance d above a dielectric plane. If we remember what a dielectric is a material where the electrons are actually bound to the atoms in that material. It's not like a conductor where the electrons are free to roam about and can move to one side of the plane or the other. In a dielectric, all the electrons are restricted in their movement and therefore can only move slightly off of where their atom is, and in this way, it'll actually induce a polarization in the material. Let's set up the problem. We'll start by drawing in our Cartesian coordinate system, where we have z, y, and x directions, and we'll put a dielectric medium in our xy plane everywhere where the distance z is less than 0. So the dielectric plane is in the place z less than 0, and the dielectric is linear and has susceptibility chi sub e, and that is a property of this dielectric. And then we'll place a positive charge q, a distance d, above this xy plane, so that's at position 0, 0, d. And what we want to do in this video is find the force that is on this charge positive q, this distance away, induced by the dielectric. And of course this force is going to be attractive because this positive charge will induce a negative surface charge on the dielectric plane, and in this video we'll be finding out what is that induced charge and what is the force felt by this positive charge. So in order to start off the solution to this problem, we'll be looking directly at the dielectric material. So we know that it's a uniform linear dielectric material with susceptibility chi sub e, and we'll put it only in the xy plane for z less than 0. Now, we know that the positive charge q will induce a surface charge sigma b on this dielectric plane, and this surface charge will be proportional to the polarization in the material, and n hat, which is the unit vector pointing perpendicular to the dielectric material. Now, because we're in the xy plane, we know that n hat will be pointing perpendicular to all points on this plane, which is essentially in the z hat direction, if we make them equal like this. So we know that sigma b will actually be p dotted with z hat. Now, if the electric field is not too strong produced by this positive charge q, we know that the polarization for a linear dielectric material is related to the electric field based off of these two constants, epsilon naught, and the susceptibility chi sub e. So, if we're to include these together, we have sigma b is equal to p dotted with z hat, which is equal to epsilon naught chi sub e, e dotted with z hat, which will pick off the electric field component in the z hat direction, and we end up with Ez. So our final induced surface charge we'll be looking for is epsilon naught chi sub e times the electric field in the z hat direction. Now we know that there will only be an induced surface charge sigma b that's bound on the surface of this dielectric material because there is no embedded charge within the dielectric material itself. Our only free charge is positive q, which is above the dielectric plane, a distance d, and because there's no free charge within the dielectric material, then we'll only have rho b on the surface, a surface-bound charge, which leads to a sigma b of induced charge, which we'll be finding using this equation. So we'll start by finding what is the induced surface charge on this dielectric. And of course, this is sigma b is equal to epsilon naught chi sub e times the z component of the electric field. Now this z component of the electric field is that which is at z is equal to 0, right where this dielectric starts in the xy plane. Now, if we're to draw our point charge q here, a distance d above the plane, we know that this charge will induce an electric field at any point on this dielectric surface, and this will be at position r, script r, and it will be a distance r in the xy plane, where r is the square root of x squared plus y squared in terms of position. So we'll be looking at the electric field component of this positive charge q that is on the surface of this dielectric at this point, which is a distance r from the z-axis, a distance d above the xy plane, and this script r here is the position that we're looking at of this electric field. Now, this electric field Ez will have two contributions. One from this positive charge q, which we just saw, EZQ, and then it will add linearly with the contribution from the induced surface charge. So this is the case that's different than just a conductor, because this dielectric will actually hold a charge, it will hold a polarization, which itself contributes an electric field. And we'll say that is Ez sigma b. So in order to find what is this electric field component Ez, we need to look at these two components separately and then add them together. So we'll start with the charge component, positive q, and we'll say that this contributes an electric field E is equal to 1 over 4 pi epsilon naught, the charge q, over this position vector r squared. And of course this will be in the negative z hat direction. And it's negative because it's a positive charge, and so the electric field will move away from the positive charge down in this direction at the plane. So we'll have that Ez is in the negative z hat direction. Now, if we're able to work through this, we can say that our z component Ez is of course negative 1 over 4 pi epsilon naught q over r squared. And we'll have this factor cosine theta. And what this cosine theta term does is it's able to pick off the z component of our electric field. So we'll say that this angle theta is made there with respect to the z-axis. So if we're looking for the z component of the electric field, by taking the cosine of theta, this will take off that component of the electric field. Now we just need to figure out what is our r vector and what is our cosine theta. So we know that r, from this diagram using the Pythagoras theorem, r squared, because it's the hypotenuse, is going to equal d squared plus r squared. And cosine theta, if we use our trig rules again, we have as the adjacent side, which is d, over the hypotenuse, which is r, which is equal to d over the square root d squared plus r squared. And so if we plug both of these into our electric field component Ez, we have that the contribution from the positive charge q of the electric field z component on the dielectric plane will be negative 1 over 4 pi epsilon naught q times d, if we include q and d from the cosine theta, over our r squared term, which is d squared plus r squared, added in this exponential component here, which is to 3/2. And therefore, this will be the contribution of the electric field from our positive charge q. So we just found that the electric field contribution from our point charge positive q was Ez sub q is equal to minus 1 over 4 pi epsilon naught q times the distance d of the positive point charge above the electric plane times d squared plus r squared to 3/2, where r squared is our usual polar coordinates, r squared is equal to x squared plus y squared. So all that's left to do is to find the electric field contribution from our induced surface charge sigma b. If we remember, the electric field produced by a plane of charge is sigma over 2 epsilon naught times the normal vector to that plane of charge. Here, sigma will be our negatively induced surface charge over 2 epsilon naught, and our normal vector n hat, because our plane is in the xy plane, will be simply the z hat direction, as the electric field will point perpendicular to the plane at all points. So this makes it easy to pick off our z component of the electric field, as the entire electric field is in the z direction, and therefore our contribution to the electric field from this induced plane of charge is Ez is equal to negative sigma b over 2 epsilon naught, where again this negative sign comes in because it's a negative induced surface charge, and therefore the electric field will point towards the charge. So if we go back to our initial equation, sigma b is equal to epsilon naught times chi sub e, and our entire contribution to the electric field in the z component will be this charge component q and our induced surface charge component sigma b, so we can add them together and end up with minus 1 over 4 pi epsilon naught q times d for d squared plus r squared, so 3/2, plus this negative sigma b over 2 epsilon naught. And the next step will be to solve for this induced surface charge sigma b, which is more challenging in this case because we have a sigma b on the left-hand side of the equation and we have a sigma b on the right-hand side of the equation. So now all that's left to do is to solve for our induced surface charge sigma b. We'll start by noticing there's epsilon naughts that can cancel in the numerator and the denominator of both of these components of the right-hand side. Then we can bring this right-hand side over to the left-hand side, remembering to include our susceptibility chi sub e. So we have that sigma b from the left-hand side plus sigma b times chi sub e over 2 is equal to, if I bring in the chi sub e to this bracket, over 4 pi qd over d squared plus r squared to the 3/2. So again, all I did was bring the sigma b, the induced surface charge, over to the left-hand side, including the susceptibility term. So we can factor out the induced surface charge. We end up with 1 plus chi sub e over 2 is equal to minus chi sub e over 4 pi q d over d squared plus r squared to the 3/2. Now once again we can expand this out and make this have a common denominator. If we make 2 over 2, we'll have a common 2 on the denominator here, which will then cancel with this 4 to make it a 2 pi minus chi sub e over 2 pi, and therefore sigma b times 2 plus chi sub e is equal to minus chi sub e over 2 pi qd over d squared plus r squared to the 3/2. And so we can go through our last simplification step and find that our induced surface charge, sigma b, is equal to minus 1 over 2 pi q d over d squared plus r squared to the 3/2 times this term chi sub e over chi sub e plus 2. And now, if we look at only this component of the induced surface charge sigma b, which I'll just enclose in a box here so we can really have it stand out. If we look at only this component here, we'll remember that in the method of images problem we solved before, this is the same induced surface charge that we ended up with, where we have minus qd over 2 pi times d squared plus r squared to the power of 3/2. What this means is that the induced surface charge is the same for our dielectric as it was for the conductor, with just the addition of this susceptibility term chi sub e over chi sub e plus 2. What that means is if we're able to find the total induced surface charge, qb, like we did in the previous video, we remember that this was simply the integral of sigma b over the area dA, and we ended up before with it just being minus q, which we could say was the same as having an image of a negative charge, negative q, a distance negative d below the plane. Here, however, we still want to include this factor chi sub e over chi sub e plus 2, and so our total charge, q, will be almost the same, but we'll have just this extra factor chi sub e over chi sub e plus 2. So we found that the total induced surface charge on our plane was qb is equal to minus chi sub e over chi sub e plus 2 times this charge q, and that our induced surface charge distribution was minus 1 over 2 pi qd over d squared plus r squared to the 3/2, again times this factor chi sub e over chi sub e plus 2. Now, if we remember back to the series on the method of images videos, in order to find the force felt by this positive charge a distance d above the conducting plane in those videos, we instead looked at a setup where we had the positive charge q and then image charge negative q, a distance negative d below the plane. And we used the negative charge negative q because we found that the total induced surface charge on that conducting plane was simply negative q. Here, however, we found that the total induced surface charge was negative chi sub e over chi sub e plus 2 times q. Therefore, if we use the same logic of the method of images problem, we say that instead of having a positive charge, I'll just erase this. Instead of having a positive charge q, a distance d above a dielectric plane, we can look at this exact same setup where we have a positive charge q, a distance d above the plane, and a negative charge, negative qb, capital Q here, which is our total induced surface charge on our dielectric plane, a distance negative d below the plane. And this setup will produce the exact same force as positive charge above the dielectric plane. This makes it easier to find out what is the electric field contributing to this force, as the positive charge Q will feel an electric field produced by this negative charge, negative QB. And this electric field is simply 1 over 4 pi epsilon naught QB over 2D squared in the z hat direction. And of course, 2D is the separation of these two charges in this setup. And if we are able to substitute in what is our charge QB, we end up with negative 1 over 4 pi epsilon naught, where the negative comes in from this equation, Q squared over 4D squared times our factor chi sub e over chi sub e plus 2 in the z hat direction. And now this is the total force that is felt by a positive charge Q at distance d above our dielectric plane. And it's modified by this factor chi sub e over chi sub e plus 2. So if we look at just this force here, this is the force that we found in the previous method of images video series. But if we include this factor, this will change that conducting plane to a dielectric plane in this problem. And we end up with the total force felt by this positive charge Q is minus 1 over 4 pi epsilon naught times the charge Q squared over 4D squared, where this comes from the separation of the two charges, times this factor chi sub e over chi sub e plus 2, which is due to the susceptibility of the uniform linear dielectric plane.